I have to remember not to leave here. So no one sees me leaving this podium, because these are actually recording the session at the back. So if I'm not too careful, it'll be a disaster. Okay. We need to increase the productivity of metal AM processes. Although we've done an awful lot and over the last, I think really last decade, to improve the throughput of metals AM processes, and particularly the quality, they're still quite relatively slow processes, and that can be a frustration when you're trying to scale up production. So working on developing new refinements to the AM process and also the actual processing parameters is a key part of the AMAZE project. So the primary objectives: increase the build rate of the AM process. And that's got a wide range of processes, and I'll explain about that a little bit in a minute. Extending the part size and complexity, improving part quality, and also the reduce the levels of defects and scrap in components. And finally, widening the range of proven materials. And those were the four primary tenets behind the work we conducted. Again, most of you will be familiar with metal AM processes, but you might be here and be familiar, for example, with powder bed, but not so familiar with directed energy deposition. So I'll briefly explain those processes, just so we're on the same page. So in powder bed fusion processes, we're taking a thin layer of powder, we're applying it to the surface of a table or a previous layer of powder, and we're using a heat source, typically a laser or electron beam, to fuse that powder selectively. And that's what you can see in the top right-hand corner. And the two main heat sources, say, are laser melting and electron beam melting. With directed energy deposition, it's more like a 3D welding process, where we're feeding either powder or a wire into the path of a laser to create a bead of molten material, and then using that to draw across the object to generate the part. There are pros and cons to the two processes. In fact, directed energy deposition is a well-established technique for repairing components and applying layers of corrosion-resistant or hard surface materials outside of the additive manufacturing sphere. So these are a range of machines and we've used within the powder bed activity. So we have laser melting machines from Renishaw, Fraunhofer ILT, we're using SLM solutions machines, Concept Laser partner in the project, and Avio we're using their laser melting machines from EOS. In terms of electron beam melting, primarily that work was undertaken at the MTC, and we have a range of machines. There's only one supplier at the moment of electron beam melting machines, and that's Arcam in Sweden. They weren't a partner in the project, but we used a range of their machines to make components. And then finally, there was some work on novel build strategies, and that included in-process strategies. For example, you'll see some work later on from ILT on what's called hull and core strategies, that how you actually fuse the metal in the process. And also Birmingham University undertook some work to generate parts that are then which are only partially dense, so you end up with loose powder within the center of the part, which is then fused afterwards by a secondary process. These are all ways to try and reduce the time to make metal components. So the key developments within Renishaw were to increase the build speed, improve part quality, streamline the process flow, develop new processing parameters, and to improve test procedures. Now, I mentioned streamlining the process flow. We tend to focus an awful lot on the melting process, but I've already mentioned that even in powder handling, most of the people we employ are actually dealing with the powder, processing the powder, testing the powder, because the machines themselves are automatic, but we have to then reprocess the powder. And for every 10 kilos of components, we might be reprocessing 190 kilos of powder. So you could say that's really where the production process is. And that's why we need to streamline the processes. So in terms of build rate, we've made some significant, Renishaw have made some significant headway in increasing the build rates of machines through increasing the laser power and also the build strategies. And you can see, particularly for materials, the orange line I think is for aluminium. And that's always been a slightly difficult material to process. It's quite reflective. And during the course of the program, we've actually managed to increase the build speed by a factor of 5 by increasing the laser power from 200 watts to 500 watts on the latest Renishaw machines. So you've got any comments to make? Stuart from Renishaw's in the audience, so I'm going to ask him if there's any other comments you want to make whilst we're moving.
I think the last point is important, that this is dependent on part geometry. These are simple geometries, and the more complex you get, different factors come into play for the scan strategy, the time involved. So this is pure data, an indication of what the improvement could be.
Yeah, and it has to be borne in mind that if you're making components where possible, you have to consider which orientation you'd build them in. And it's not unusual for machine suppliers to do all of their productivity numbers on flat plates, which are quite quick to build. No one likes building thin components because they have a lot of recoating time and a relatively small amount of fusing time per layer. As part of that project, we have to also make sure we get decent material properties. There was work done on Inconel 625, so a nickel alloy, and also onto an aluminium alloy, aluminium silicon 10 magnesium. It's a sort of stalwart of the aluminium materials used in additive manufacturing. And what we can see is that we can get decent densities, greater than 99.2% density for aluminium, which has always been a slightly challenging material. Good mechanical properties, examples here for Inconel 625, approaching the sort of book values for forged, rolled and annealed materials, and which is what we're aiming for. We don't want to produce castings, we want to produce properties which are closer to sort of the materials you'd see for high performance components. Any other comments, Stuart? This is not going to be an easy presentation for you, Stuart. I'll move on to somebody else's in a minute. So,
Can I leave now?
And then it's
next
fine.
one as well.
Another important thing is you have to develop in parameters. When you get a new material, you have to develop parameters for that material. And what's been really clever at Renishaw is they come up with an automated technique where you build cubes as a standard, and each cube has a different set of parameters, which is standard practice. The clever bit is that those cubes then go into a holder and they're polished and assessed automatically. And that's quite a tedious process. I know from my colleagues that have to do that over in the MTC, that this is a solution to rapidly come up with the parameters you need. What you're looking for is density values. You're looking for how much porosity you're getting. And the only way you can do that really effectively is by polishing the samples. And so there's the automatic polishing and also the automatic assessment using optical techniques. Is that a reasonable?
Yes, but that's only one aspect. With tensiles, you've got the other mechanical properties. And the more you can automate, the quicker you can bring a new material into process on the machine. And that's always going to be one of the challenges.
Yeah. As we go forward, as materials become better developed, then the amount of intense work we're doing at the moment, which is based in the metallurgy lab, in the materials labs, will tend to drop away. But we're probably talking a 10 or 20-year journey. The moment we're right in the heart of this, the biggest skill shortage we have in the AM sector is for material scientists, because there's a whole range of new materials that have been required. It's great for the metallurgists. It gives them a whole new lease of life in terms of new processing. I mentioned about powder handling, and some machines are better than others. And one of the key developments at Renishaw is that rather than take material out of a machine to then sieve it and place it back into the machine manually, the new generation of machines have automated, integrated sieving systems that allow you to reprocess the material within the machine without having to break into the machine to take the material out. And that's very, very effective. As a general rule, we don't want people to come in contact with powder or powder to come up in contact with people. So the less that we see of the powder, the better in AM processes.
Do you want me to jump down there?
Okay. The thing that's flashing in the far right-hand corner is hull and core strategy. And what you'll notice is only bordering. Well, you would have noticed if it's now actually filling in the inside. I'll restart that video so that if I can, probably can't. So what you've done, what's happened there is that with hull and core strategy, you're scanning the border and you're putting down potentially 3 or 4 layers of material before you use a higher power laser to fuse the core. And that saves time. It introduces its own levels of interest and complexity. But for some parts, particularly where you've got a bulky section, hull and core strategy is a real way of collapsing down the build cycle. So 3 layers of borders with a fine laser and then a fairly high-powered laser to fuse the core material. So as part of this part of the AMAZE project, Fraunhofer ILT, we're looking at high-powered lasers to fuse the core, low-powered lasers to fuse the edges, and completely new levels of power involved. And studying the effect of this approach on mechanical properties, the microstructure, the accuracy and surface finish of parts, and the build rate improvement. There's no point in going through this whole process and still being the same build rate. Those trials were undertaken using Inconel 718. And these are some of the results. You can see here that they were benchmarked. We benchmarked the results both in terms of properties and productivity with standard parameters. So effectively, standard machine running at 300 watts hull, the skin, and 300 watts in the core. And then looking at how we can increase the core power right up to 1.5 kilowatts. And then looking at different layer thicknesses before you scan. So if you're laying down a 30 micron skin, after two layers, you'll be doing 60 microns in the core. Or after 3 layers, you'll be doing 90 microns in the core. Or after 4 layers, you'll be doing 120 microns, right up to 150 micron layers. The guys at Fraunhofer ILT produced the samples and then worked with Airbus in Germany to actually test those results, including all the heat treatment. So this is a really significant campaign of work. And what can we see? Well, I'm going to just do the highlights here. So by applying a 1 kilowatt laser using the process, you end up with effectively a 4.9 fold increase in build speed. And then we're using the 1.5 kilowatt. That increases to 6.8 times the original fusing speed. So that's quite a step up. Now I have to, before you get too excited, that's not the whole story, because that's the fusing speed. That's not the overall processing speed. So when you actually incorporate that into the full process, your benefits reduce down slightly. But to achieve that uplift in the fusing process, which is by far the biggest chunk of time, is a significant development. And there's more What we now need to look for is applications that it can exploit this particular approach. It isn't for every type of component. If you've got a very thin wall part, the benefits tail off. But you have a component where there's bulky sections, then this is really quite a nice process. When we first mentioned this process to the aerospace industry, there was significant concern about microstructure, because you have a different microstructure for the core and the skin. And also significant worries about what happens at the interface. So you can see on the right-hand side, on the far right, we've got effectively epitaxial long columnar grains formed in the core, and on the surface, more equiaxial fine-grained structure. And that's something we have to bear in mind. When you're doing your stress predictions and your performance predictions, you have to understand and make sure that you're designing for the right properties. But I still think it's something we need to consider. I don't think it's, even for the aerospace sector, which is particularly conservative, I think it's a good process. And there was no evidence of defects between the skin and the core material in any of the samples that we looked at. If anybody here from ILT? I've got no get out of jail on that one. Right at the back. Oh, they're all sitting at the back. Okay. I might ask you some questions. Okay. These are the tensile test results, and interestingly, it's not all good news. It never is. So, if we go, in terms of properties, the first thing that you're going to get an uplift in properties with heat treatment, and that goes across the board for most AM processors. So if you're using raw components, you probably need to heat treat them to get the best properties. But also, as you're increasing the power and also the layer thickness, you are getting a drop-off in the properties, which I guess is understandable because you're altering the microstructure. And that applies both to the 1 kilowatt and the 1.5 kilowatt samples. But as long as we understand that, we can design for it. Guys at ILT, anything to comment on that, Sebastian? No. Okay. The work at Concept Laser, I'm not sure most of you are aware, but Concept Laser makes some fairly large machines. They specifically developed some of these machines for making automotive engine blocks for prototyping. And there's significant interest within the automotive sector for aluminium alloys. And a major program of work was done within Concept Laser to perfect the parameters for aluminium alloys to try and increase the productivity. Also to develop automated powder handling systems, and also include process monitoring equipment in the process. Because the one thing you don't want to do is to be making a huge engine block and find that there's a defect halfway through it. And here's some of the examples. So the first thing is that during the course of the project, through optimization of parameters, so back in 2013, we were just effectively just a few months into the program, we had a 40 centimeters cubed per hour build rate, and that's now increased to more than 60 centimeters cubed per hour. The density values are in an acceptable range for the automotive sector, for aluminium 10, silicon 10 magnesium, using a 1 kilowatt laser, and that's an example of the component that was produced on the larger machine using that material. Again, there's been significant work done within Concept Laser in terms of powder handling. In this case, it's not a powder handling within the machine, it's an integrated system that sits outside the machine in terms of sieving and also blending and powder storage. So at the end of the process, the powder ends up in a sealed container, hopefully with no intervention and contact with the operator. I should say, particularly important if you've got a large machine. I'm not sure how much powder is used in the 1000 DAR machine. Is anybody here from Concept Laser? Go on, guys. How much aluminium powder would you have in your machine for a full build?
Well, aluminium, I think about 200 kilograms.
200 kilos. So you don't, yeah.
Inconel about a ton or something.
Wow. So you wouldn't want to be doing that by hand sieving that. That wouldn't be a very pleasant job. So this is why you have to start to automate the process. Any other comments from the guys at Concept Laser? You're happy with that? Yeah. Okay. So I have a piece of work we've done at the MTC focusing on electron beam melting processes. So in the case, we have quite a range of different machines, and we delivered the first large, what was then the A2WT, which stands for wide and tall machine, which was effectively like the A2 but grown both in height and width. And these machines will take 200 kilos of titanium powder at a time. They're processing with around about 3 kilowatt laser, electron beam. And what we wanted to know was whether or not the claimed higher productivity and yet better surface finish and resolution was achieved, because in most cases you don't get an increase in build speed without sacrificing something. And in this case, it seemed to be a fantastic arrangement where we could actually have better quality parts and actually faster. As part of the AMAZE project, and I particularly feel proud of this work because it's quite hard to get standards, international standards to be developed. It developed a suite of benchmark parts. Most of you are familiar that when your previous benchmarking parts that are used to assess processes are normally a big monolithic slab of material. And that's great, but they're very expensive to make. And for most users, you don't want to have to make that benchmark part in its entirety. And what we've come up with is a suite of benchmark samples, each one tailored to assess a particular parameter, whether it be surface finish or accuracy. And that approach now is now the basis of a new international standard being developed through the ASTM F42 ISO TC 261 Joint Committee 51, which is developing this into a test artifact standard. And to say there was quite a lot of concern that we'd stick with the same benchmarking approach, but both the European organisations involved in that work and the Americans feel this is the right approach. So the suite of parts we've got will allow us to test accuracy, surface finish, resolution, metallurgy, and defects and productivity as well. So one thing we found straight away is that it's quite a significant improvement in productivity, and that's in part driven by the cooling cycles. So you see the orange boxes there. Within the RCAM process, it's a hot process. The material's being held around about 790 degrees C. So it takes time to warm it up, and it takes time to cool it down. And in an argon atmosphere with relatively low conductivity powders like titanium, that process was taking 5 hours after the process has been completed to get to the point where we could open the door and start to process the powder and take the parts out. What RCAM have done is introduced a system where the build chamber has a cooled block, which comes in contact with it and draws the heat out of the build chamber, and that's led to a 40% reduction in the overall time, but a 5-fold reduction in the cooling time from 5 hours down to 1 hour. And that actually seems a relatively simple thing to do, but you have to do it. And by thinking about productivity, this has made a significant difference in the throughput of the machines we've got. In addition to that, there's been some work done on developing scan strategies, and say that the machines are significantly faster. This image just shows the sort of relative comparison between the A2XX in blue and the Q20, and you can see in every case, apart from metallurgy and defects, which the Q20 scores higher marks. So for accuracy, for surface finish, for resolution, and productivity, the Q20 outperforms the A2XX. Another thing we were doing with the work at MTC was to develop an electronic build chamber. So one of the things is that at the moment we're processing 200 kilos of powder to produce 10 kilos of parts, and have to recycle 190 kilos of material. What we're trying to do is to think, can we generate a build chamber that's shaped around the parts that we're making? And so the first trial was to do a small build chamber, so to go from this large 380 millimeter high, 350 millimeter diameter build chamber, to be able to process a small amount of material and see what the effect was on the productivity. So we looked at the powder utilization, the time saving, the materials development, the decrease in build cost, and also and we also had to develop new preheating strategies. So this is the change we made to the machine. It was at the time quite distressing. We just got a brand new machine, and we were changing it to do this work. So we produced a smaller build chamber that sits inside the machine, and also altered the hoppers so they weren't supplying the full width of the powder. They were only supplying the powder over the strip required for that build chamber. And what you'll see, for those that aren't familiar with the electron beam process, you have to pre-sinter to stabilize the powder, otherwise it becomes volatile in the machine due to electron pickup, and it disperses it within the machine. And this is now on the new build chamber. So normally it would be bigger than the whole screen at this scale. So it shows that this new build chamber works, and some of the samples we produced with it are in the far right-hand corner, showing that we've actually made samples to compare the properties. When we compare the build time and cost savings, it's quite significant. You know, we're saving in terms of, for example, the amount of material overall. We've gone from 80 kilos of powder required for the old machines to just 14 kilos in the new machine. So it's a saving of 60 odd kilos of powder. The overall processing time is quicker because we're not having to preheat the whole area, and that makes a significant saving. We're also reducing the raking time, the cooling time. So this simple idea has significant benefits, and what we'd be doing in the future is have a machine with multiple apertures for the parts you're making. So to conclude this, we've made hardware changes to the machine. We've actually optimized the parameters to enable us to use this build chamber. We've developed 3 different builds which were successfully achieved using the new system. We reduced the preheating and pre-sintering cooling time, and just from our own benefit, it allows us to develop new materials. If we're having to be faced with buying 200 kilos of material to do one test, it's a bit of an expensive process. It's not ideally suited to materials development. Whereas in this case, we can now test a few kilos of material and start to develop the parameters. We're also reducing the amount of waste powder we generate, because the powder itself degrades in the process. So the less powder you use in the process, the less waste powder you generate. And we're also reducing the build time. So in the future, we'd see customized chambers for particular products being developed. And we're already seeing that to some extent. A productionized AM machine will be based around the products it makes. Some work at the University of Birmingham on in situ shelling. Some of the people involved in additive manufacturing for a while might recognize the patent from Joe Beeman at the University of Texas and Dave Burrell. Rather than make a completely solid object by fusing it, in this approach, we generate a shell with loose powder inside the part. Then that's processed by powder hipping, afterwards to generate a fully dense part. This patent now actually has lapsed. And one of the problems you have with the process is, first of all, you need to generate a skin which doesn't have any, it has to be completely hermetically sealed, so you can draw a vacuum on the powder. And also, you need to be able to predict the distortion during the subsequent hipping process. So what Birmingham have been doing is working on those two areas of work. And so with their M2 over at Birmingham, they've developed a way of making pore-free canisters. And then they've been doing some work on generating a simulation of the actual, I hope this will run. I have to try and, okay. So apparently that was a simulation of how much it consolidates. So the whole idea is that this powder's going to consolidate during the hipping process. It's going to be heated and squeezed to make a fully dense part. What we then do is change the geometry of the part to compensate for that distortion. So it allows you then to produce parts of the right size. And you start by doing a simulation, so you're not having to do too many iterations. Another alternative is just to scan the component with a structured light scanner and do the compensation that way. Here's some of the samples produced and the trials done. And this was a collaboration between Birmingham and also University of Manchester to look at the sort of process and how much consolidation we were getting. There's the metallurgy behind it, so the properties were good. You can see that you're getting an equiaxial core, so the powder inside of the skin processes to produce a uniform grain structure part, and the actual skin is this tends to reflect the fact that we're using a laser process to fuse it. And this is an example that was produced within AMAZE. We couldn't find a part that really was ideally suited to the process. Again, like the hull and core strategy, you need to have a bulky component, and we're trying to design parts that aren't bulky because we know it's expensive. They're expensive to make. This would allow us to build parts that at the moment are just not cost effective by additive manufacturing. These parts, I think, are on display next door. I've mentioned powder processing. I need to get a move on and to talk a little bit about the directed energy deposition processes. These are sort of 3D welding processes, laser and powder, and wire plus arc processes. So just to as a bit of a background, in terms of laser plus powder processing, you can either have a coaxial head where the powder is fed in a cone to a focus and melted with a laser, or you can have a side feed head where the powder is fed through almost like a straw into the path of the laser. And this work's been done by Fraunhofer ILT, looking at how they can increase the build speed of these processes. They are already quite fast, but for large components, you can never be fast enough. All this work was done with Inconel 718. Here's their test setup, big coaxial head here, and what they did is they took their coaxial head and went from a fine head and then engineered a coarse head for high deposition rate. So it went from a 2 kilogram per hour head to a 5 kilogram per hour head. And And for large parts, in fact, they use this for a component for a component from Airbus. You don't need the resolution. You don't need the resolution you're getting with a fine head. The fine head's particularly good for repair work. Here's some of the properties. I won't go into any details, we're running behind. But with all the work we did, we had a significant materials test campaign in the background. And then another application was to look at high-powered laser, but in this case, putting down a track of powder rather than using a coaxial head, so a side feed and with a high-powered laser. And this is now achieving 10 kilos per hour deposition rate. Fairly big track, so a 14 millimeter by 2.5 millimeter track, an 11 kilowatt laser. Conclusion, so deposition rates during the project were increased, 2 kilowatt fine laser, fine deposition head, then a 5 kilowatt per hour head, and then right up to a 10 kilogram per hour head. Not all good news, there's still some work to be done in terms of properties, but the direction of travel is what's important here. Work done by ARIPA, you'll see some of the parts that ARIPA have been made as part of demonstration parts next door, looking at improving the machinery, the processing, getting reasonable mechanical properties, and then making the demonstration parts. There's no point in making demonstration parts. These are not paperweights. These demonstration parts are being tested, being subjected to testing, and therefore they have to be treated as though they were production items. So this is the new machine developed by ARIPA in the project, increasing its capacity in terms of size of parts and its weight, the weight of components, and improving the control. A new cladding head with a 2 kilowatt laser to increase the build speed, and also at the same time improving the cooling of that head. Aha, I have an error message. Hold on a second. Bear with me. So on the last few slides now, so here you can see that, this has been a journey for all the guys developing processes in the project. And we have to be honest, when we first started making parts, we had defects in them, and they have to be, we have to refine the processing parameters to improve, for example, lack of fusion, large, what looks to me actually not really pores, but lack of fusion defects again. And also tearing. One of the big problems we have with these high-rate processes is a lot of stress in the parts, and they can become detached from the build plates. And that's what you see here, this tearing problem. What ARIPA did was they developed new parameters, which they then generated good quality components, and they've used those to make demonstration samples, which you'll see next door. Also build strategies to try and improve the deposition rate, but also to reduce the chances of loss of fusion defects by putting one layer down and going through 90 degrees, putting the next layer down and going through 90 degrees again. That helps to lower the risk of a build-up of lack of fusion defects and also lowers distortion. And overall conclusions, they've made some large parts. In fact, the part next door, although it's very impressive, is actually a half-size component. The full-size components are actually currently being prepared for testing at ESA. Some work done at Trumpf. There's a couple of slides and we'll be finished. Objected again to try and improve the throughput of high-rate DD processes. They've actually developed in the program two new heads, one based on standard optics, so a high rate, high powered head which is used and scan and moves across the surface of the part being formed, and then this new approach, which is actually a scanning head. The head itself scans, so you actually inside have a scanning system that allows you to increase the scan speed. And so for the head on the left, 6 kilowatt laser depositing around about 600 centimeters cubed per hour. I can't do the math on that in terms of deposition rate. And on the left, on the right, we've got the scanning head, slightly lower deposition rate, but useful for certain things. And there's a video here that hopefully it'll play if I push the button, I guess. Okay. So that's an existing component. And what Trump have used it for is putting another layer onto that part. So, for example, it doesn't need to be additive manufacturing. It could be applying a layer of corrosion or wear-resistant material. I think that's quite neat. You know, we've seen a lot of that within the project. Example from Cranfield. I'll just show the video because it's quite a nice video. I won't show it all. It's a bit lagging it to play at all. That's a shame. I'm not giving up on this. Sorry, guys. What you would have seen is a 6 meter long part being generated. There you go. There's a certain amount of time lapse in this because you can see people running around in the background. But we shouldn't take it away from the fact that the work that's been done at Cranfield. That is a big component. Okay? It's a simple component at the moment. But so the issue is about scale. How do we make large parts? They're building this spar. It's actually, I think it's a double-sided component, I think it is. But in fact, you can clad two components at once. And that's an ambitious project. We've seen some examples from China. That even trumps the stuff that's been done in China in terms of size of parts. And there's some of the materials. They'll be talking about those, I'm sure, next door. And that's the group at bit of work at Norse Titanium. They've developed their parameters for processing titanium, again by plasma transferred arc and wire. And interestingly, and I think this is probably a pretty telling thing, they've generated this new factory for making components, and they've recently been awarded status to actually, you know, they've had the first part qualified. We're not supposed to name the company that they've done it for, but I suspect it's a large American aerospace OEM. There's not that many of them, I guess. So those, you'll see some of the parts outside in the display area. The work that's been done within AMAZE has helped provide the foundation for Norse to achieve this. Because what you can't afford to do is take risks with a production part. You have to develop the parameters offline, and that's what AMAZE has allowed them to do, is to perfect the parameters, particularly the intersections between walls, to reduce the amount of defects. That's the finished, that's actually a smaller version, I think, but that shows what it looks like when it's been machined. Last two slides, I promise you. We've done a lot of material testing in the project, a big material test campaign. And that shouldn't be underestimated. That was coordinated by the guys by Gary Moore at Bombardier in Belfast. Fatigue, tensile properties, all of that data, and it's been undertaken in a very rigorous way. There's traceability from powder right through heat treatment to final component. And that data has then gone into the AMAZE database that's been developed by Granta. And I think this is a great output from the project. And what we'd like to think about is a way of using this database potentially as a European database for future projects. So if Granta's doing a demonstration at the break, the lunch break, and if you want to see how that software works and what the schema they've developed, then please seek them out. said it'd be late. 5 minutes, sorry. Any questions? In terms of the detail, it's a plasma transferred arc system. I think it's been purchased from a company called Feronius, and they've then stung on a robot. I didn't recognise the flavour of robot. I think it was an orange robot. Anybody know what an orange robot? Who makes orange robots? ABB.
They are KUKA robots.
KUKA robots. Are they? Okay. Are you from Cranfield?
Yes.
Okay. Any awkward question for Cranfield? There's a lady here, 1, 2, 3, 4, 5, 6 rows up, who can answer all your questions over the lunch break. Okay, thank you.
We need these signs on each head.
Yeah, we do actually.